Then, so welcome back. So in this session, we've got 3 or stroke 4. There's a merged talk, but we've got 3 10-minute talks. So please put your questions in the Q&A as they come up, and mention who your question is addressed to, just to help us when we do the questions at the end. But we won't. We'll wait till the end of all 3 talks before we take the Q&A. Okay, so the first one is by Yanbao Zhang from NTT Basic Research Lab, and he'll be telling us about security proof of practical quantum key distribution with detection efficiency mismatch. So please go ahead.
Thank you for the introduction. So this is a joint work with Patrick, Adam, Jie, and Norbert. So first, let me briefly motivate why we study efficiency mismatch. The first obvious reason is detecting efficiency mismatch always exists in practice. For example, if we would like to measure the polarization state, we need 1 polarizing beam splitter and 2 detectors. Due to fabrication, it is difficult to make these 2 detectors have the same efficiency. Also, the coupling efficiencies of these detectors can depend on their alignment and their setup. This will also cause efficiency mismatch. The second reason is, besides polarization, photons have multiple degrees of freedoms. And for example, so for photons can be in different temporal mode or spatial mode. A detector can respond to a photon differently, depending on the degrees of freedoms of the photon. So if you can manipulate these additional degrees of freedoms, so you can effectively induce efficiency mismatch. People have demonstrated if you can completely control the efficiency mismatch, so you can learn every possible result of Bob. So in that case, perfect intercept and recent attack exist. In this work, we will study the effect of efficiency mismatch on security proof. Before introducing our method, so I would like to first mention there exist security proofs which can handle efficiency mismatch. However, all these proofs assume the system arriving at Bob contains at most 1 photon, but in practice, so the system received by Bob is an optical signal, which naturally described by an infinite dimensional system. So this assumption is not justified. And to handle infinite dimensional system, we just introduce a map called squasher. By applying this map, we can treat Bob's system effectively as a finite dimensional system. Inside of this squasher, when the photon number is high, we flag out the Bob's measurement results. So if you can access the squasher, you can learn every possible result of Bob. So for this reason, we would like to ensure the state lives in a small photon subspace with a high probability. So the next step of our method is just try to bound the photon number distribution. We develop method for this purpose. By combining these 2 steps with the numerical approach for security proof, we can formulate an optimization problem in order to lower bound the secret key rate. In this case, the measurement operators of Bob encode the efficiency mismatch information. So that's why we can study the effect of efficiency mismatch on security proof. So next, I will briefly illustrate our results. So first, we consider a case without mismatch. We would like to study the separate effects of transmission loss and detection loss. The transmission loss is over the public channel from Alice and Bob. Since the public channel is accessible by Eve, so this loss is not trusted. The detection loss is inside or above the lab. Because above the lab is secure, so this loss is trusted. Here we just fix the overall efficiency to be 10%. You can see the key rate and does depend on how much loss is trusted. So in general, we can distill more secret keys if the trusted loss increases and the untrusted loss decreases. Next, I will study the efficiency mismatch case. So we consider two detectors. There are mismatch between the efficiencies of these two detectors. For security analysis, we can assume Bob's system has at most 2 photons, or we make a security analysis without such assumption. So we just use flag state squasher. If you compare these two results, you can see by making assumptions on Bob's system, we can overestimate the key rate. We can also consider the mode-dependent efficiency mismatch. By comparing the results with the previous one, you can see mode-dependent mismatch helps you to attack QKD system. The results shown here is for active detection case. Our method can also handle the passive detection case. The details are available in our paper, or you can watch the YouTube video. Thank you very much.
Okay, thank you. So we're going to take all the questions at the end. So we'll now move straight away to the second talk. So, okay, it should be just coming up. So yeah, the second speaker is Ian George from the University of Waterloo, telling us how to do numerical calculations of finite key rate for general QKD protocols. So please go ahead.
So thank you for the introduction. This is joint work with Gia Lin and Norbert Luckenhaus. So let's just get started. So the motivation is pretty straightforward. We now implement QKD in real life, which means we have two problems. One, we have finite resources, which means we need to consider finite size effects. And two, we're going to have imperfections in our devices, which might mess up some symmetries of the given protocol. And so this poses a problem because when we want to achieve tight finite key rates analytically, we normally need certain symmetries in the observations or in the construction of the protocol. And so our solution is a numerical method that doesn't require these symmetries to get tight finite key rates. It uses Renner's framework for finite size effects, which is to say the min entropy framework, and it extends the numerical method for tight asymptotic key rate to the finite regime. So the results of the paper are an improved analysis of the parameter estimation subprotocol for finite size, a general numeric method for the tight finite key rates, and an investigation of these tools for different protocols. But I'm just going to consider one example to show how it works in this quick talk. So the idea of the improved parameter estimation is that when you want to calculate the finite size key rate is you want to construct some set which is going to ignore the states that Alice and Bob will almost always abort on. This is basically the composable security talked about earlier for the parameter estimation subprotocol. The problem with this is that the method for constructing this set traditionally basically suggests that Alice and Bob throwing out information makes them more secure against Eve. The reason for this is because the way you construct this set is by considering the number of joint outcomes of Alice and Bob during parameter estimation. So if you think of BB84, in principle, there are 16 joint outcomes of Alice and Bob, but you could just consider phase error, which has 2. And so if you just consider the phase error, then your key rate could go up because you've shrunk the size of the set S mu. And this is a problem because it's not intuitive. So we show that this isn't true, that throwing out information can't help you. And the way we show this is by saying, oh, well, it turns out you can take your data and process it in different ways and retain the same security while considering this. So with that idea in mind, we then generate a general numeric method for considering finite size. The basic idea stems from the asymptotic solution, which is you want to calculate this optimization problem of minimizing the conditional von Neumann entropy over some set S, which is the set of states which satisfy some asymptotic observations. And then you start with some guess of the attack rho naught, and then you move towards the optimal attack of the asymptotic problem. And then at some stopping condition, you take that point, you linearize it, and you get the dual and go to the boundary of the set. And this always gives you a lower bound, which is to say that it's reliable. And in the case where rho equals rho star, then this is a horizontal plane. And so you get the true answer. And so it's also tight. And so in the finite key case, you get the same sort of idea. Again, you have this minimization over a conditional von Neumann entropy, but this case, it's over this set S mu that we just talked about. And so again, we can write this as a semi-definite program, and we show that we can do this without introducing any looseness in the problem. And furthermore, we show that we can handle both collective and coherent attacks, which is an important point in the finite size regime. So we'll just quickly consider one example of where this numerical method is useful. So if you think about BB84, Alice is going to send Bob these 4 signal states on the block sphere, but you could imagine that the channel is going to apply a unitary rotation about the y-axis. And so Bob actually gets these 4 states instead, which is to say that in some sense he's received this rotated block sphere, which you could think of as reference frame misalignment. But if they have sufficient parameter estimation, that is to say they have the fine-grained data, they can actually use this in parameter estimation to undo the unitary, which makes the key rate stay the same as if the unitary didn't happen. However, if they did the coarse graining, just considering the phase error that we discussed earlier, then they wouldn't be able to do this. And so this is a problem, at least at the asymptotic limit. So we sort of explore this. So here we see this numerically. If you have these rotated results, the phase error has a better key rate in the small signal limit. But as the number of signals you can use goes up, the fine-grained statistics does better. And this has to do with the fact that you basically can undo this unitary. But then as we discussed earlier, we could consider multiple ways of coarse graining our data. And so numerically, we can consider both. And this gets us a better key rate in all regimes. And this is a major advantage of the numerical method because it's able to handle this optimization problem, which would be difficult analytically. We also note in the case where you accept multiple frequency distributions in your protocol, which is often an overlooked concept in finite key analysis in papers, then this is also a thing that our numerics can do. And this is, again, an advantage because in general, if you have some sort of asymmetric behavior, it's not obvious what the worst frequency distribution in attack would be. And so our numerics allows you to consider this. So that's the gist of it. There's a lot more, so you might want to look at the total talk. But to summarize, we improved the analysis of the parameter estimation subprotocol. We constructed generic numerical method for determining the finite key rate of QKD protocols represented in finite dimension Hilbert spaces, not just this qubit protocol, but qubit MDI, and also optically implemented protocols that can be represented in finite dimensional Hilbert spaces. And then lastly, we consider some examples using this and consider when it might be useful to use our numerical method. We also hope it could be useful for investigating side channels in the finite regime. So thank you.
Okay, thank you very much. And so now we'll move to the merged talk. So the speakers have also, in this case, merged their location, which is very handy. So I think the first part of the talk will be by Ilaria Agnilusha, if I say that correctly, and then it will be followed by part by David Bako. And the talks are firstly overcoming qubit-based QKD with efficient high-dimensional encoding, and then towards high-dimensional quantum key distribution over a 2-kilometer long multicore fiber. So please go ahead.
Okay, so thank you for introducing. So this works deals with high-dimensional QKD, that is to carry more than 1 bit per photon. And in particular, the main idea of this work is to simplify the experimental setup for high-dimensional QKD. In particular, we address the 4-dimensional protocol with time-bin encoding. So in contraposition with previous works, we didn't use the time of arrival basis, but we decided to test this alternative four-dimensional basis, where we have only two time beams combined in each state. So thanks to this efficient time beam encoding, it is possible to simplify the experimental setup at the receiver. As here we have to project in each basis, we need only one interferometer. And these two interferometers can be overlapped, as you can see in the figure with the experimental setup at the receiver. So thanks to this efficient time beam encoding, and also by adding an active basis choice at the receiver, it is possible to notably simplify the experimental setup of the QKD system, which requires only two single photon detectors. So we have high dimensional QKD with only two single photon detectors, as you can see here at the receiver. Our results are reported here and in this graph, and are compared with a two-dimensional time beam protocol that we have tested in the same work by employing mostly the same experimental setup. And the enhancement of the secret rate that we have demonstrated here shows that this new scheme that we proposed can be a cost-effective solution for practical high-dimensional QKD with single-mode fibers and time beam encoding.
So the second part of the talk will be to use different degrees of freedom, in particular space encoding, to demonstrate high-dimensional over a special type of fibers that are the multicore fiber. So multicore fibers are well used and well known for the classical communication communities, and actually in Italy at L'Aquila there are deployed multicore fibers of different distances, and they are well used for database, so inter-database communication or intra-city communications. So the idea of this work was to demonstrate that it was possible to achieve let's say a good secret rate generation by using a different degrees of freedom. So during the last years, what we have been investigating was we present this concept of using space encoding, but we had a different kind of problems. In particular, we tried to address the problem of phase stabilization. So we can see at this experiment as a sort of a superposition between different cores in a multicore fiber. So up to now, what we have demonstrated was a few meters of distance between the transmitter and the receiver. But with this work, what we did was we combine a phase lock loop in order to keep phase stability together with a QKD setup. So here on the bottom of your left, you can see the QKD, the setup that we used. And in particular, we use two different wavelengths, one for the quantum light and the other one for the stabilization signal. So within the same systems, we are able to propagate the stabilization signal without any modulation by using a smart, let's say, a smart phase loop. And we also send through the same system a modulated QKD scheme at 600 megahertz repetition rate. So here we highlight the two mutually unbiased bases that we used. In particular, you can see that we always use superposition between two cores. And on the plot on your top right, you can see a stability measurement that we achieved actually the last month. So all the spikes, the red spikes that you can see are basically the moment where the phase lock loop lose the stabilization of the systems. But automatically we recover down to a good point. So as you can see, our systems is able to achieve a very, very good quantum bit error rate. The overall quantum bit error rate is 4%, 4.2, for more than 1 hour of measurement. Before conclude, let me thank all the people who has contributed to these 2 talks that we are presented. In particular, also would like to thank David Ruska and Hugo Spindem for University of Geneva. And thank you for your attention.
Okay, thank you very much. So, well, we've finished all 3 talks in a very good time. So I'm now going to hand over to Li Chen, who's going to organize the Q&A.
Right, thank you. So the talks are open for question and answer. So far, there's been no question typed in, so we'll give a few minutes for people to type in, and please indicate which speaker you have the questions for.
May we ask a question?
Go right ahead.
So for Yan Bao, so actually we were discussing the paper that you presented, and we are asking ourselves, can you use a similar approach to prove a security if you have different dead time of the detectors?
Or different dead time. Okay. Okay, that's not a efficiency mismatch. That's
I mean, I don't know the answer. That's why, I mean, we are asking also, yeah. Because I think it's, I mean, probably from a technical perspective, it could be that an eavesdropper could use this different dead time to for getting information on the key, but maybe it's possible. I don't know.
Yeah, I do not have a clear answer now, but I think it's possible. So our method is can handle not only efficiency mismatch, but I mean the main idea is we can try to as long as the measurement operator is block diagonal in a photon number basis, then we can apply this kind of squasher, the flag state squasher, to map it to a finite dimensional system. So if the measurement operator still have this block diagonal structure, considering this detector time, dead time, different detector dead time, so it's possible, but I'm not quite clear how to model this, how to write down the measurement operators considering this dead time, different dead time. Yeah.
Okay.
Yeah, thanks. Yeah, maybe we can investigate it.
Yeah, thanks for your question.
Okay. Now we do have a few questions. One is from Lavi. Go ahead. I enabled you to talk, so go ahead and ask your question.
Yes, thank you. I would like to know for Ian, you mentioned the RFI example, and I was wondering if you could use directly the RFI quantity as in the original RFI QKD paper, like average of XX squared plus etc., instead of using phase error and full statistics, because that quantity is basically capturing this invariance because of the rotation. So maybe it would be faster to reach the best key rate.
So I guess the one concern from the equation you've put there is that it's taking the squares of expectation values, and normally when you think of the way you do finite size effects, you want to just take the expectation values of each joint outcome. So to answer your question, no, I haven't looked at that, but that's okay. An interesting point.
Okay, I see. Okay, thank you.
Thank you. Next, we have a question from Dev, and the question is directed to Davide. Go ahead, Dev. You can talk and ask the question. Okay, maybe I'll ask. It's for Davide, asking about the refractive index of multicore fiber. I assume that's the refractive index of the core, or maybe the index difference.
So yeah, you're right in the sense that the standard multicore fiber, they have more or less the same refractive index as a single mode fiber. So to say something more of a point is, one important measurement for quantum communication is the crosstalk between different cores. It means that when you are sending the light into one core, how much light can you get in the other cores? To reduce this effect, it's possible to slightly change the refractive index of some of the cores in order to have less crosstalk between them. So, but it really depends on how big you want your multicore fiber, so, and how many cores do you want, and this kind of things.
Okay, thank you. Yes, I also saw a question from Frederic that is directed towards Ian. Go right ahead, Frederic.
Yeah, so I was wondering, so in your optimization problem, is there a reason why you don't always reach the optimal solution? Like it looks like a convex problem, that it doesn't look like there's anything preventing you from always finding the optimal.
So there's a couple of points. The first one is we're really paranoid about getting a lower bound so that it's reliable. And so when you numerically solve things, you're never going to get the optimal to begin with. The other thing is because of our methodology, we wind up sort of converting from the conditional entropy into a relative entropy, and then we simplify it to something that is nonlinear. So then not nonlinear, non-convex. So then we do have to do this progression. There's an explanation in the Winnick paper. I could send you a link if you'd like.
Okay, so it's somehow not actually convex in the version you're doing.
Because of our simplifications.
Okay.
Yeah.
Okay, great. And perhaps I could ask a question. It's a question for Ilaria regarding the time-bin encoding. I know the high dimensional, the purpose is to have higher capacity. But in terms of the time-bin encoding specifically, you still need fairly high speed modulation for your Z bases. So is there a practical advantage over the qubit case?
Okay, thank you. So regarding this point, that is why we, in the same work, we have tested also a two-dimensional scheme with time-bin encoding. So we have tested a two-dimensional QKD with the same time-bin duration as the four-dimensional. And we created in this condition an enhancement of the secret key rate. So even if there is the same time-bin duration, that means that the two-dimensional state preparation rate is twice faster. We demonstrated an enhancement. So the answer is yes, there is a gain in the overall system.
Mm-hmm. So is that the curve that you showed was the 2-qubit, with 4D and 2D curve that you showed? I noticed that for the 4D, it has an advantage in the short distance, but then it drops off more quickly. Can you give an intuitive answer to why it is the 4D case drop off more quickly for the larger?
In general, it applies for in every kind of high dimensional encoding, because the fact is that high dimensional is advantageous if you are in the saturation regime of the single photon detector. So at a certain point, when your dark counts become not more negligible, we have that the error rate increases faster if you are in a high dimensional system than if you are in a two-dimensional one. So a random dark count is more damaging if you are in a high dimensional protocol. So the region where you gain in the secret rate is in the saturation regime of single photon detector. Okay.
Okay. Thank you very much. That makes sense. Okay. Let's see. I don't think we have more questions, so I think we'll end this session and